last lecture we were looking at the hydrogen molecule, the quantum chemistry of hydrogen molecule, and we began the discussion with the two methods or the two approaches which are commonly employed for studying the hydrogen molecule, namely the valence bond method and the molecular orbital method. And after introducing the molecular orbital method a bit, I switched over to the original proposition of hydrogen molecule, the solutions for the Schrodinger equation, which was proposed by Heitler and London, and we just started writing down the equation for the energy when we ran out of time. So let me recall the last equation that we wrote down in today's lecture. This is on hydrogen molecule continued. Let me go back and recollect the expression for the energy using the valence bond wave function. The valence bond wave function is for the two nuclei called A and B, denoted A and B. Let me just use that, yeah. And the electrons denoted 1 and 2 with the electron coordinates R1 and R2. The valence bond wave function was what you see here, 1 by 2 square root of 2 into 1 plus s square times this wave function, psi 1 as A R1, psi 1 as B R2, plus the electrons being indistinguishable, their coordinates switched with psi 1 as A R2, psi 1 as B R1, and the energy expression for this wave function was given by the integral psi star psi here, the psi is again, and with the Hamiltonian in between. The Hamiltonian is that which I wrote as we would calculate, because the way it is reorganized gives us some simple things immediately. This is the Hamiltonian, and then we have the psi star psi, that is psi star h psi, and the normalization constant is already there in the form of 1 by 2 into 1 plus s squared. So this is the integral that we wanted to calculate, and at this point I stopped. So now let us start looking at this integral term by term. The way I have grouped it, you can see that there are two wave functions here, products of two wave functions, but two terms here, which I call as maybe term 1 and term 2. And the Hamiltonian, I have blocked this in the form of three groups. The group for the Hamiltonian for electron in the atom 1, the Hamiltonian for the electron in the atom 2, plus the potential energy terms involving the electron 1 being attracted by the nucleus 2, electron 2 with the nucleus 1, and the electron-electron repulsion, the nuclear-nuclear repulsion, all these things being grouped into a separate block. So what you have is 1, 2, there are three Hamiltonian blocks, and 1, 2, you can call this also 1 and 2. So you have the integrals of various kinds today, if we have to write it, and let's also call this as maybe H1, H2 and H3, three blocks. So a total of how many terms we have? We have the integral term 1, H1, term 1. We have term 1, H2, term 1, and the last in that will be term 1 H3 term 1. So, this involves the first term on both sides, and likewise you have 1 on the left, 2 on the right, 2 on the left, 1 on the right, and 2 on the left and 2 on the right. So, into 4, a total of 12 terms are there. Okay. But we do not need to evaluate all the 12 terms, because we see that by symmetry some of these terms are equal to the others. So, let us look at the first one. What I call as term 1 is this integral 1 by 2 into 1 plus s square integral psi 1 as a or 1 psi 1 as b or 2 multiplied by or with the Hamiltonian operator minus h square by h bar square by 2 m e del E 1 square minus E square by 4 pi epsilon naught or A 1 acting on the wave function psi 1 as A or 1 psi 1 as B or 2 d or 1 d or 2, both are 3-dimensional integrals over the electron coordinates r1 and r2, which is nothing but the first term in this block here, the first part of the Hamiltonian H1 and the first term here. Okay. It is very easy, because you see this is the Hamiltonian for the electron in atom 1, hydrogen atom 1, acting on the wave function for the electron in the hydrogen atom 1 psi 1 as A or 1 corresponds to the electron associated with the atom A, and therefore, this is nothing but the H psi is equal to E psi for the hydrogen atom, and since we involve the 1s orbital of atom A, we have E1SA. So, this will give you E1s atom A psi 1s A or 1, okay, which is this term. Hamiltonian acting on the wave function gives you this E1 as A. Okay. And the rest you know that it is going to be normalization, because what is left over is the moment the Hamiltonian operation is taken as a constant with the eigenvalue, what is left over is the wave function psi 1 as A R1, psi 1 as A R1 D R1, and then the wave function which is not changed, which is psi 1 as B R2, psi 1 as B R2 D R2, and therefore, that is 1. So, the answer here is simply E1 as A. Gives the integral gives. So, term 1 is 1 by 2 into 1 plus s square times E1 as A. Sorry, it is not A, we have just a superscript A as we write here. What about the next one? The next term that I would like to do look at is term let us call it term 2 for energy, involves the same wave function 1 by 2 into 1 plus s square integral psi 1 as A or 1 psi 1 as B or 2 with the Hamiltonian acting on the left, the Hamiltonian being minus h bar square by 2 m e del E2 square, the second electron, minus E square by 4 pi epsilon naught or B2 as we have written, acting on the wave function psi 1 as A or 1 psi 1 as B or 2 D or 1 D or 2. Okay. Again, this is exactly the same as the previous term, except for this being on the electron 2. Okay. That is, this is the Hamiltonian for the electron associated with atom 2 and acting on the wave function associated with the electron in atom 2 psi 1 as B, and the answer for this is going to give you E 1s, and B or A does not matter because B or A essentially tells you that which atom, I mean both hydrogen atoms are equal. So, E1sB and E1sa are the same, but acting or multiplied by psi 1sB or 2. And the rest you also know that it is going to be normalization, because once the Hamiltonian's action on the wave function is given by the energy, the wave function is normalized. So, this will also give you exactly the same result that we had, which is 1 by 2 into 1 plus s square E1sB. Okay. Now, the third term in the first block that we wrote, the third term for the energy is whatever is remaining, namely 1 by 2 into 1 plus s square integral psi 1sa or 1 psi 1sB or 2 with the Hamiltonian, the remaining term, which is minus E square by 4 pi epsilon naught times 1 by or A2 plus 1 by or B1 minus 1 by or 1 2 minus 1 by or AB. Okay. All of this multiplied by the wave function psi 1sa or 1 psi 1sB or 2 times d or 1 d or 2. Okay. Now, you can clearly see that the terms can be easily blocked out as 1 by 2 into 1 plus s square. Let us put a bigger bracket. You can take the terms to be psi 1sa or 1, psi 1sa or 1 and minus E square by 4 pi epsilon naught 1 by r B1. This is the same thing as the Coulomb integral that we calculated for the hydrogen molecule ion. All of this correspond to the electron 1, but associated also with the atom 2, the nucleus 2 or B, and therefore, this is the Coulombic energy for the electron at the atom B due to the electron density of the electron being associated with atom 1 at the position R1. So, this is the charge density, it is divided by the distance, so it is a Coulomb integral. By the same token, let me remove that, okay, or let us have it that way. This is already marked or B1 and psi 1sa R1. Now, let us mark the same thing with the next item. If you look at psi 1sB or 2, E square minus E square by 4 pi epsilon naught or A2 psi 1sB or 2 d or 2, if you do that, that is exactly the same J integral, except that everything is now shifted to the electron 2. So, these two terms contribute identically, and then the remaining two terms, the remaining product, of course, you can see that psi 1sa R1 in this case, psi 1sa R1 d R1 will be 1, and therefore, you have this whole thing is the electron 1 some density divided by a distance associated with electron 1 coordinate, electron 2 density psi star psi divided by the distance associated with electron 2, nucleus 2 or nucleus 1, that does not matter, it is a charge density by distance, and then you also have psi 1sa R1 psi 1sa R1, that is electron 1 density square density, electron 2 density psi 1sB R2 psi 1sB R2, 2 electron densities divided by 1 by R1 2, which is obviously the Coulombic repulsion between the two charge densities electron 1 and electron 2 separated by a distance R1 2 and summed over. Of course, that integral tells you that you are summing over all such things. Therefore, this whole thing is Coulomb, and the last term RAB, we do not need to worry about it because it does not have electron coordinates. Therefore, it will merely give you the answer minus E square by 4 pi epsilon naught 1 by RAB, does not change anything. therefore it's an addition to the total energy. So this whole integral, which when it is blocked out into three forms, appears like psi 1s a r1 squared divided by with a minus e square by 4 pi epsilon naught, or b1 d r1 and multiplied by, of course, psi 1s b r2 squared d r2. Okay. This is of course 1. So this is the first term in the J integral, and the next term will be exactly the same but for the electron 2, 4 pi epsilon naught. So what you have is psi 1s b r2 squared divided by r a2 d r1 d r2 multiplied by the integral psi 1s a r1 square d r1. Okay. And the last, of course, the two terms is minus e square by 4 pi epsilon naught integral psi 1s a r1 squared psi 1s b r2 squared divided by r12 plus, of course, sorry, plus d r1 d r2, all inside this big bracket, the curly bracket, and the last term, which is plus e square by 4 pi epsilon naught into 1 by r a b, because whatever is left over is integrated to 1 due to normalization. So this is the whole thing is called the J or Coulombic integral. The calculation of these two terms, the Coulombic integrals involving electron 1 at a distance from the second nucleus and electron 2 at a distance from the first nucleus, these two are exactly the same as the H2 plus molecular ion Coulomb integral calculation. Therefore, there is nothing new. But what is new here is this additional term, the electron-electron repulsion, which is something now we have to carefully evaluate. You see that it is centered on two different nuclei, A and B, and also it is a 2 electron repulsion integral. So it is a 2 center 2 electron repulsion integral. This requires a bit of time, and I will not do that. We will simply call it by the Coulombic integral. In an assignment, I will probably show you how to calculate this. It is somewhat tedious to evaluate. Okay. And the other thing is, of course, the nuclear repulsion energy, which simply adds to the total energy, and as the nuclei are further apart, this energy becomes smaller and so on. So you see that the calculation of the first term, if we go back, the first term, namely 1H11, 1H11, H21 and 1H31, where 1 is this wave function, 1s a r1, 1s b r2, gives you in summary E so far it gives you 1 by 2 into 1 plus s square E1 s a plus E1 s b, both are identical, plus j. Okay. There are 9 more terms that we need to evaluate, namely psi 1s a r2, let us take the second group of terms, psi 1s b r1, and of course it is multiplied by 1 by 2 into 1 plus s square here, with the Hamiltonian as H1 plus H2 plus H3 acting on psi 1s a r2, psi 1s b r1, d r1 d r2. Okay. This is the second group of the three terms that you have to evaluate, and it should be obvious to you, if not after my pointing it out, that this term cannot have any value different from what we just discussed, because you have the wave functions with the coordinates r1 and r2 interchanged, but it is integrated over all the coordinates of r1, all the dr1 and all the dr2, and the Hamiltonian is of course symmetric to the interchange of these two coordinates, because it is about the two indistinguishable electrons, kinetic energy, potential energy, and the nuclear potential energy. Therefore, the Hamiltonian is symmetric with respect to the interchange of 1 and 2. The wave functions are only interchanging the coordinates, and dr1 and dr2 are sort of dummy variables when you do the integration. Therefore, this is exactly the same as what we had calculated, namely 1 by 2 into 1 plus s square. It is also E1s A plus E1s B plus J. No difference. What you call as R2, what I call as R1, does not matter. But consistently, if you call something as R2 and the other is R1, you must consistently do the algebra, and you see that the choice is gives you that these two terms to be identical. Therefore, 6 terms. By looking at the symmetry of this calculation, we can immediately say that these 6 terms give you the simple result. What about the other 6 terms? Now, let us look at the first set, namely 1 by 2 into 1 plus s square integral psi 1s A or 1, psi 1s B or 2, with the 3 Hamiltonian terms H1 plus H2 plus H3. Now, acting on the other wave function, namely 1s A or 2, psi 1s B or 1, D or 1, D or 2. Okay. Now, H1 is associated with electron 1. Please remember, it is minus h bar square by 2 me del E1 square minus E square by 4 pi epsilon naught, or A1 is del 1, that is the electron 1. Electron 1 Hamiltonian acting on the electron 1 wave function on the left. Hamiltonian is a Hermitian operator. Therefore, it acts on the function on the left side or on the right side, giving you at the most complex conjugate values, but being a Hermitian operator, it gives you real eigenvalues. And therefore, H1 acting on psi 1s A on the left hand side is going to give you psi 1s A times E1s A. This will give you E1s A again, except what is left over is, after this H1 acts on, what is left over is E1s A times psi 1s A or 1, psi 1s B or 1, D or 1. If you look at this integral, psi 1s A or 1, psi 1s A or 1, psi 1s B or 1, D or 1. This Hamiltonian has given already the E1s A, and the remaining is of course the integral psi 1s A or 2, psi 1s B or 2, yes, psi 1s A or 2, psi 1s B or 2, D or 2. Okay. Now, this is the overlap integral for the two wave functions associated with the two nuclei with the electron 1. Therefore, this is S A B, and this is the overlap integral for the electron 2 associated with the two nuclei A B, and this is also S A B. Therefore, the answer that you would get for the first term is E1s A times 1 plus S squared A B. That is only the H1, the first term. I do not need to tell you now, H2 will give you exactly the same answer, because it is all with reference to the electron 2 Hamiltonian, and the electron 2 Hamiltonian acting on the wave function for the psi 1s B is going to give you again E1s B. So, the answer here will be plus E1s B times 1 plus S square AB, and the last term that we are left with, namely term 3, let us write that out, is 1 by 2 into 1 plus S square integral psi 1s A, I think I had R1, yes, R1 psi 1s B R2 with minus E square by 4 pi epsilon naught 1 by R, what did we do? Yeah, A2 plus 1 by R B1 minus 1 by R12 minus 1 by R AB, all of this acting on psi 1s A R2 psi 1s B R1 D R1 D R2. If you look at this and separate this into coordinates of the electrons, what you get is exactly similar things to what you had as the K integral in the H2 plus ion, that is the exchange integral. Let us write that out. It is psi 1s A R1, and the coordinate R1 is of course minus E square by 4 pi epsilon naught R B1 psi 1s B R1 D R1. This is one type, and the remaining term, which is psi 1s A R2 psi 1s A R1 psi 1s B R2 D R2. Okay. This is the first of the 4 terms that you have for the B1, and likewise you can write for the A2 involving psi 1s B R2 and psi 1s B or psi 1s A R2. Therefore, this whole thing is now called the exchange integral K. Of course, multiplied by 1 by 2 into 1 plus SAB square. Okay. So, term 2, or the group of terms which involve the wave functions, the 2 different wave functions, psi 1s A R1 psi 1s B R2, and the wave function psi 1s A R2 and psi 1s B R1 with the Hamiltonian in between, give you the energy E1s A, the energy E1s B, both multiplied by 1 plus S square, and of course the rest of it being simply called as the exchange integral K. So, the answer for the second group of terms is the energy now, again partly, is, if you go back to the expression here, we had E1s A, this is into 2, so we should write 1 by 1 plus S square E1s A plus E1s B plus J, that is for the first 2 terms, and first 2 or 6 terms together, and now what we have is 1 by 2 into 1 plus S square E1s A S square, sorry, plus E1s B S square plus K. Okay. And the last group of 3 terms is only going to have these 2 wave functions interchanged. Let us go back to the integral. Yeah, in this integral, this wave function and this wave function will be left right interchanged, and with the Hamiltonian, of course. So, it is not going to give you any different result, it is going to give you exactly the same result as we had just now calculated, and therefore the answer is again into 2 for this part, and so this 2 goes away. Okay. So what is left over is then the total energy now is E psi Vb plus is therefore 1 by 1 plus s square times E 1s A into 1 plus s square plus E 1s B into 1 plus s square plus j plus k. Okay. And of course, you can cancel this out with that, and so what is the total energy? What the total energy is, it is E 1s twice, because A and B refer to basically 1s electron hydrogen energy. So twice E 1s plus j plus k divided by 1 plus s square. Okay. This is the energy associated with the state. One by 2 into 1 plus s square square root psi 1s A or 1 psi 1s B or 2 plus psi 1s A or 2 psi 1s B or 1. Okay. So we have the Coulomb integral and the exchange integral that we have here, and we have the overlap integral square, and the energy of the valence associated with the valence bond wave function, the average energy associated with the valence bond wave function is in addition, the difference between that and the sum of the 2 hydrogen energies if the hydrogen atoms did not interact with each other. If you call that as delta E plus, then we can write this we can write this as delta E psi MO plus. If we have to do that, that is E average minus psi MO plus the 2 E1s, and that is given by j plus k by 1 plus s square. Okay. Both j and k are negative, s is positive, and therefore you see that the delta E plus is now negative, which means that as the hydrogen atoms come together as a function of one of the RAB, the internuclear distance, you see that there is attraction, and until the RAB becomes sufficiently small for this whole thing to become positive, the energy is decreasing, and therefore there is an optimal distance of RAB at which the energy is minimum, and this is what is called the bonding energy or energy of the bonding orbital, of the valence bond orbital. Okay. The calculation of J and the calculation of K in the case of hydrogen molecule involves one additional step, namely the electron repulsion term. Electron repulsion term, in addition to the terms that we calculated earlier for the hydrogen molecule ion, but they can be done, and I am not going to discuss the magnitude of that. They are all fairly straightforward integrals, and when you do that, the final result E or delta E plus delta E for this psi MO plus as a function of or AB internuclear distance can be plotted, and I am going to give you the results that others have done, calculated earlier. So if you plot the delta E psi MO plus as a function of the internuclear distance or AB. What you see is you calculate the graph looks like that, and this is 0, 0. That is, this is where the absolute energy scale, it is the sum of the two hydrogen 1s energies, namely minus 27.2 electron volts. You remember that the 1s electron of the hydrogen atom is stable by minus 13.6 electron volts, and when you have two such hydrogen atoms non-interacting sitting next to each other, the total energy of the system is minus 27.2 electron volts, and that is the baseline with respect to which the energy of the valence bond orbital is less, and therefore, this distance where this is the minimum, the energy is the delta E is the maximum, this distance, this is the equilibrium bond distance. Okay. We use the valence bond orbital with the plus between the two wave functions, namely R1 and R2. Psi 1 is A R2, psi 1 is B R1. Now, if we use a minus combination, the normalization constant can be shown without much algebra that it is 1 plus or minus s square. That would be the wave function, and if you calculate the energies delta E plus, it will turn out to be delta E for the minus combination psi MO minus, it will be j minus k divided by 1 minus s square. So, if we plot this value delta E minus, that is for the psi MO minus, in the same graph, let us use a different color. Okay. So, if I plot delta E minus psi MO minus, then the graph shows no minimum, which means that when the energy is calculated for the antisymmetric combination, please note that this is an antisymmetric combination with the minus sign. If you write this 1 by square root of 2 into 1 minus s square, psi 1 is A or 1, psi 1 is B or 2 minus psi 1 is A or 2 psi 1 is B or 1. This wave function is antisymmetric with respect to the interchange of the coordinates of 1 and 2, because when you interchange R1 and R2, the wave function becomes a negative of itself. Therefore, this is an antisymmetric combination, and this antisymmetric combination gives rise to no stability. You can see that the energy is always above the what is called the minimum in the scale, which is the sum of the two hydrogen atoms. Therefore, in that state, the electrons, if they are placed, the electronic energy is greater than the sum of the two hydrogen atoms, and therefore, this is what is obviously not even non-bonding, it is anti to the bonding, and so this combination is known as the anti-bonding valence orbital, anti-bonding orbital. But it is interesting now to go back and look at what I said regarding these two wave functions in the last lecture, that the overall wave function for the two electrons, which involves not only the spatial coordinates R1 and R2, but involve also the spin coordinates, namely the alphas and betas, the wave functions of the two electrons. You see that the antisymmetric combination in the coordinate space obviously requires the spin wave functions to be symmetric. So, there are three spin wave functions, namely alpha 1, alpha 2, alpha 1 beta 2 plus beta 1 alpha 2, and beta 1 beta 2. There are three of them, and in the absence of any external magnetic field, or in the absence of the perceived absence of the electron orbital spin angular momentum interactions. Okay, we assume that it is not there. In that, in the absence of those, these three states are obviously degenerate, the spin states are degenerate. Therefore, the antisymmetric combination has three possible states, degenerate states, whereas the symmetric combination, which we took with the plus sign, has only one possible spin state, which is antisymmetric, and that is called the ground state. So, the ground state of the hydrogen molecule with the two electrons in the same molecular or the bonding orbital, the valence bond orbital, if you think of that, the ground state is such that it is a spin 0 state. Both the spins are paired, and therefore, in a magnetic field, the spin quantum number will be 0 for that. And the antisymmetric state has the spin quantum number is corresponding to the triplet state. The total spin will be 1, and there are three possible states for a spin 1, namely 1 0 minus 1, and those 1 0 minus 1 states are the states given by alpha 1 alpha 2, alpha 1 beta 2 plus beta 1 alpha 2, and the last one beta 1 beta 2. So, you see that this kind of approach, when it is meshed with the spin angular momentum states, gives you a reasonable picture which does not violate any fundamental principle, particularly the Pauli's exclusion principle. And so, let me summarize this with the correlation energy diagram that we have. Namely, if we start with the two 1s states for nucleus A and nucleus B, the symmetric combination gives rise to an energy which is, let me put it in such a way that I should be able to draw that within this screen. So, the symmetric combination, this difference is in our calculation, it is j plus k by 1 plus s square, and the other state is j minus k by 1 minus s square. And so, you have the two electrons in this state, which is a spin 0 state for the spin, and this is given by 1 by square root of alpha 1 beta 2 minus beta 1 alpha 2 times psi mo plus times. If on the other hand you have the two electrons excited, then what you have is the two 1s orbitals of the electron A 1s B, and the lower state and the upper state. If we do that here and connect that, these states originate from these two 1s wave functions, and that is the connection, and this state also originates from this two 1s, and that is a connection. So, if you put the two electrons here, then you see that the electron has to have three possible states. It is a triplet state. Okay. And you have to see that you have to put in the, it is a threefold degenerate in terms of in the absence of any spin interactions, and the electrons can be with the plus plus or plus minus and minus plus and minus minus. So, this is a triplet state, the excited anti-bonding state, and the bonding state is a singlet state. Okay. There is a whole set of data available, and I would like to refer you, for example, for some preliminary data to the book by Macquarie, and I think there is a table in chapter 9. I would not write those things, please refer to the textbook, for variation in different approaches, variation between approaches, along with the references to the original papers is given by Professor Macquarie, quantum chemistry. I am sure you can find them elsewhere as well, but it is a ready reference for you in case you need to know where things are. and I think it is table 9.1, table 9.1, okay, and results of various calculation. This table contains many data, various calculations of H2 for H2. There is a reference to the valence bond method, 2 different ways of doing it. There is also a reference to the molecular orbital method, 2 different ways of doing it. Then you remember that in the molecular orbital approach we identified the valence bond contribution, and then we had this H minus H plus and H plus H minus contribution, namely the electron 1 and the electron 2 both associated with the 1s orbital of the hydrogen atom A. The term corresponding to that was psi 1s A or 1, psi 1s A or 2, and then we had the H plus H minus, which has the electron, both the electrons associated with the atom B. So if you do that, that is called the ionic contribution, and so valence bond plus some ionic contribution with different weightings, different combination coefficients, what are the results and so on. So you see that this is a very rich field for the electronic structure theorists to provide what are called good guesses of the molecular orbital wave functions, finally with those energies which are very close to what we measure experimentally as frequencies. Therefore, these energies are such that the difference between these energies should give you the match between the experimental frequencies and the theoretically calculated values. And I believe the valence bond plus ionic contribution and another method which I will discuss later, known as the Hartree-Fock method, are very close to experimental results. So there's a whole list of things about the hydrogen molecule that you would like to refer to, and some of these things would be put up in my lecture notes along with the PDF file. But the basic calculational aspects I have exemplified here with some blocking of the terms, and I hope that it is helpful to you in understanding how to do such molecular bonding calculations. So in the next lecture we move on to other homonuclear diatomic molecules, and we would do more qualitatively the bonding and the anti-bonding orbital picture. We will draw that, and we will draw what are known as the electronic correlation diagrams or correlation of energy diagrams. We will look at for both the homonuclear and heteronuclear diatomic molecules, and later on we move on to what are known as simply the polyatomic molecular chemical bonding picture. Okay. Until then, thank you very much.